We're good.
Y equals a to the x power is an example of an exponential function. If a has an absolute value greater than 1, it is an exponential growth.
Okay, go ahead and pick somebody else.
Mark.
If the absolute value of a is greater than 0 but less than 1, it is an exponential decay. An exponential growth function approaches infinity as x approaches infinity. Here.
Alright, exponential growth was with a constant percent increase over a specific time period can be modeled with the function a parentheses t equals a parentheses 1 plus r. 1 plus r is called the growth factor.
An exponential decay function approaches 0 as x approaches infinity. Exponential decay with a constant percent decrease over specific time periods can be modeled using a times t equals a times the quantity 1 minus r to the power t.
1 minus r is the decay factor. The x-axis acts as an
Asymptote, yep.
asymptote for both functions. That was 2 sentences still.
To graph an exponential function, select the values for x and solve for y, then plot the points. Transformations at times x equals a times b to the x minus h plus k.
Okay, so let's look at the decay and the growth equations. So it's not a times t. Okay, this is function notation, right? Right.
Some people say at times x.
Okay, shh. So this is your growth function. So in your word problems, if it says that it increases or something is, growing, you're going to use the growth function. Okay, and then your decay function is really the same thing, except the only difference is instead of 1 plus r, your parentheses is 1 minus r. So you're subtracting the rate instead of adding the rate. So the key for this a of t is actually your y, right? This little a is your beginning amount. So it represents the starting amount. The r is your rate of increase or decrease, and that's usually a percentage. So, but whenever you substitute it in to your equation, you need to change it to a decimal. So it's a percentage as a decimal. You always change the percentage to a decimal when you multiply with it or do anything with it. And then t represents the time. Now sometimes if it says, like one of your word problems says something about a number of games, so you would want to use, change values for this t to get a graph. That's like your x. Okay, so you could use, let's say the games are you have 15 games. So the values you use for the t, you don't have to use 1, 2, 3, 4, 5, 6, 7. You don't have to use every single one. You can skip around and maybe use like 3 and 6 and like that, just to get a few values. You don't have to use 15 of them. Okay, so let's graph an exponential growth, and we're going to make it a very simple graph, so it's going to be like a parent function. This one's not on your paper. We're going to graph y equals 2 to the x power. Okay, and we're going to use a table of values, and then we're going to plot the values, and we're going to draw our graph. So, got my x and my y. And since this is a parent function, I'm going to use -2, -1, 0, 1, and 2 for my x values. When you get some transformations, then you want to use different numbers for the x, but for a simple graph like this, we're just going to use -2 to 2. So let's substitute in -2 for the x. Y equals 2 to the -2 power. So what is that negative going to do to your base? You guys remember from last semester? It flips it over, right. So this is actually going to be y equals 1 over 2 squared. Okay, so when x is negative 2, y is 1/4. When x is negative 1, that means y is going to be 1/2. When x is 0, what is y going to be? 1. When x is 1, y is 2. And when x is 2, y is 4. Okay, so let's graph those points. Negative 2 and 1/4, so that's just like this. It's almost 0. Okay, negative 1, 1/2, 0, 1, 1, 2, and 2, 4. So your graph is going to look like this. And it's a growth because on the right side, it keeps going up. As your x value increases, your y value is increasing. So as x goes to infinity, your y value goes to infinity. And that's what a growth function does. Okay, so is there any value for x that I can put in that will make y 0? No, there's not. So that's what they are calling an asymptote, is when your graph gets closer and closer to a certain value. In this case, it gets closer to 0, but it's never going to reach it. So the x-axis acts as an asymptote, and the graph is going to approach that asymptote, but it won't cross it. Okay, now every once in a while, for a horizontal asymptote like this one, your graph will cross the horizontal asymptote. But if it's vertical, it will never cross it. Okay? And we're going to do vertical asymptotes later, but just so you know, sometimes the graph can cross that horizontal asymptote. All right, so the domain for this, restrictions on your x value. Are there any restrictions?
No.
No, so it's going to be all real numbers. And your range, there is a restriction on the range, isn't there? What does y have to be?
Greater than 0.
Okay, so all values of y, so that y is greater than 0. Okay, any questions? Okay, let's do another one. Let's look at number 2. Now the reason I wanted to do this equation at the first is because number 2 is the same basic thing, but you're adding 1 on the end. Two to the x plus 1. Okay, so I can use the same table. My x values, I can use the same x values. It's just that for my y, I have to add 1 to each y. So when x is negative 2, y is going to be 1 1/4, which is 5 over 4. When x is negative 1, y is going to be 1 1/2, which is 3 over 2. When x is 0, y is going to be 2. When x is 1, y is going to be 3. When x is 2, y is going to be 5. Okay, so let's graph this one. Sketch this graph. Negative 2 is 1 1/4. Negative 1 is 1 1/2. 0, 2, 1, 3, and 2, 5. Okay, so looking at those two graphs, what happened to the second one? It moved up 1 unit. That's right. So anytime you have something that's added or subtracted at the end of your equation, separate from what your x is, that's going to shift it up or down. So that kind of helps you know where your domain, or where your range, is going to be starting. Okay, so your domain, again, is going to be all real numbers. There's not a restriction on the x value, but your range now, because of that plus 1, y has to be greater than 1. So this base value that they give you when it's a growth function is always going to be greater than 1. This base function is, or this base value is going to be a positive number. Okay? Now sometimes they'll have a number in front that's negative. Okay, for transformations, there's your general form for transformations. So this value for A can be negative, but your base is always positive. Okay? Any questions? Okay.